Let's turn our attention now to section 6.5, Determinants of Matrices. We've talked about addition, subtraction, and two types of multiplication for matrices, multiplying two matrices together or a matrix times a scalar. We haven't talked about division, nor are we going to exactly. Division by a matrix is not exactly defined the same way we would define division of a number or the division by a variable. Division for matrices is substantially more complicated. So here, we're not going to talk about how to do it. In our last section, we're going to talk about how to determine whether or not a matrix could be divided by. Again, division is the wrong word, but it's roughly the right idea. So let's go ahead and talk about what's called a determinant of a matrix. Oop, I don't know how to spell. There we go. Determinant of a matrix. So the determinant of a matrix will, among other things, determine whether or not you can invert it. That's the proper term. If the determinant of a matrix is not 0, then the matrix can be inverted. That's kind of like saying we can divide by it. Again, division is the wrong word, but it's more or less the right idea. So here, I'm going to stop using the improper word. I'm going to stop using division, and I'm going to start using the proper name. If the determinant of a matrix is not 0, then that matrix is invertible. Okay. That'll take the inverting will take the place of dividing for matrices. Well, if it's not 0, then it's invertible. If the determinant is 0, then that matrix is not invertible. So the determinant determines whether or not you can invert. It doesn't really matter what the determinant is, as long as it's not 0. If it's not 0, then yeah, you're fine. If it is 0, then no, it's not invertible. Okay, so this determinant, what is it? Well, obviously, it can either be 0 or not 0, which means it's going to be a number. Okay, so how do we find the determinant of a matrix? All right, so let's say we have the matrix M is equal to 2, 5, 3, negative 8. Okay. First of all, the symbol for the determinant is it's going to look like the same. It's going to look like the symbol for the absolute value sign. It's two bars like this. This is read as the determinant of M. Just like that. Okay, so the determinant of a 2 by 2 matrix is very, very short and sweet. All you're going to do is you're going to multiply these two numbers together. This is called the main diagonal. The main diagonal is the one that goes from the upper left down to the lower right. So let's multiply those together. 2 times negative 8. Just like that. Now we're going to multiply these two numbers in the other direction. In the secondary diagonal, in the backwards diagonal, the one that starts in the upper right down to the lower left. And that's going to be 5 times 7. Like that. I may as well put all of these in parentheses. And then once we have those products, we're going to subtract them from each other. So here, 2 times negative 8 is negative 16. Minus 5 times 7 is 35. And if I take negative 16 and I subtract negative 35, I get negative 51. So that's it. That's my determinant. The determinant of that matrix is negative 51. For any 2 by 2 matrix, finding the determinant is fairly short and sweet. You multiply these two numbers together. Separately, you multiply these two numbers together, and then you subtract. Again, why should that be the case? It's not something we go into very much. There is an entire field of math dedicated to talking about, well, partially talking about matrices. That's called linear algebra. It is a branch of algebra, but it's its own separate thing. For now, suffice it to say, determinants are labeled this way. This is the correct way to do it, because if it is done this way, a bunch of other things in math and physics work out. If you don't do it this way, then a bunch of things don't work out. So we do it this way because it's necessary for other things to work. But since we're not in a linear algebra class or in a physics class, suffice it to say, here's the technique that we use to find the determinant. All right. So here, give this a try. Let's say you have the matrix N is equal to, let's say 2, 6, let's say 1 and -3. All right, so go ahead and pause the video, find the determinant, and once you're done, go ahead and unpause the video. All right, so we're going to find the determinant. Remember, the symbols are the same as the absolute value bars. This is the determinant of n. And here that's going to be 2 times -3. And that's going to be 1 times 6. And then we're going to subtract. So that'll give us -6. And that'll give us another -6. All right, -6 minus 6. And that'll give us -12. All right. So in this case, this has a determinant that's not 0. So this matrix is said to be invertible. And here, this has a matrix that's not 0. So again, n is invertible. If your determinant is 0, then your matrix is not invertible. Okay? So for a 2 by 2 matrix, things are nice and simple. Okay, what if it's not a 2 by 2 matrix? Well, then it's slightly less simple, but it still relies on this kind of a pattern. So let's talk about what we mean when we talk about a cofactor. Well, actually, I'm getting ahead of myself. First, we should define what we mean by a minor. Then we'll go ahead and bring in cofactors. So let's go ahead and consider a bigger matrix. Let's say something 3 by 3. Okay. I guess I should mention that too. The determinant of a matrix, I wrote that up here and I never finished the thought. The determinant of a matrix is only defined for square matrices. When we say a square matrix, we mean a matrix whose dimensions make it a square, meaning it has the same number of rows as columns. So here this has 2 rows and 2 columns, 2 rows and 2 columns. These are called square matrices. Likewise, we would have, if we had a bigger matrix, we would have something that was 3 by 3, or 4 by 4, or 5 by 5. If you don't have the same number of rows and columns, then you don't have a square matrix. And if you don't have a square matrix, we can't talk about the determinant. We only talk about determinants of square matrices. Okay? So now let's say we have the following 3 by 3 matrix. Let's say we have 2, 4, 2, 1, -3, 0, and -5, 5, 1. Let's make that a -1 there. Okay. Now, when we discuss the and I suppose I should give this a name. So let me call this the matrix, I guess just A is fine. So let's say the matrix A. All right, now, let's say I'm going to find the minor of A. Okay, so what does that mean? Well, a minor is a number that's associated to one of the numbers on my matrix. And you say, what do you mean? Well, let's look at an example here. I'm going to go ahead and just pick one of the numbers on my matrix. It doesn't actually matter which one, but I'm going to go ahead and pick the number 4. Okay? So here, I'm going to go ahead and find the minor of this number. The way to find the minor, so find the minor. Here, notice this is in row number 1, column number 2. So I wouldn't really say find the minor of the number 4, because here you might have the number 4 multiple times. Here we want to be specific, so I'm going to name it by its position. So find the minor. The way you write down the minor of that number is going to be M for minor, and this is in the first row, second column, M12. So now the way you find the minor is you're going to essentially imagine that the column that number's in isn't there, and you're going to imagine that the row that it's in isn't there either. Say, okay, I've imagined that they're gone. So now what? Well, notice that there are 4 numbers that are not in either the row or column. So if these are all gone, imagine that you have a matrix made up of just those 4. The minor M1, comma 2 is the determinant of that matrix that's left. 1, 0, -5, -1. I'll say that again. The minor of this number, you're going to ignore this column and this row, and you're going to be left with a smaller matrix. 1, 0, -5, 1. 1, 0, -5, 1. You're then going to find the determinant of that. Okay, cool. So now, the determinant of this is nice and simple, just like we saw above.
Sorry, I'm not sure how to help with that.
Well, thanks anyway, Google. That was a little strange. Anyway, we're going to multiply these two together. So 1 times -1, and then we're going to multiply these together. That's going to be 0 times -5, and then we're going to subtract those. So that's going to be -1 minus 0, which is -1. So here, the minor of that number is that number. Okay? Let's do that again. Go ahead. You should give this a try. Go ahead and find the minor given by M, let's just say, what do I want to do? Let's go with 2, 3. Find the minor M23. All right, so give that a try. Pause the video, and once you have an answer, go ahead and unpause, and we'll go through it together. All right, so the way that's going to work, go ahead and find the position 2, 3 in your matrix. Okay, well, that's this one right here. Second row, third column. Okay, so now I'm going to go ahead and pretend that the column that number is in, and I'm going to pretend that the row that it's in are gone. So if this is gone and this is gone, then I'm left with a smaller matrix, 2, 4, -5, 5. 2, 4, -5, 5. And the minor is going to be the determinant of that matrix. All right, so let's go ahead and do that. That's going to be 2 times 5 minus, that's going to be -5 times 4, which will give us 10, double negative makes that a plus 20, which is 30. So the minor of that number is that number. The minor of this number is this number. So now that we see what a minor is, we can go ahead and use this to find the determinant of a bigger matrix, of a 3 by 3. Okay, so 2 by 2 is just like this, and the minors are also the determinants of 2 by 2 matrices. It turns out that by finding the minors, by defining the determinants of these smaller 2 by 2 matrices that are in here, we can put those together a certain way to find the determinant of the full bigger matrix. And this will always be true. If you have a 4 by 4 or a 5 by 5, you can always find minors to find the determinant of that big matrix. Okay? So let's see how that works. Here we're going to stop with 3 by 3 matrices. We're not going to go 4 by 4 and 5 by 5. This technique that we're going to talk about would still work for much bigger matrices, but if you can do 2 by 2s and 3 by 3s, that's fine. That's all that we're really looking for right now. Okay. If you want anything with to work with bigger matrices, of course, that would be in a different course. So let's go ahead and define how a bigger matrix, how we can define its determinant. So let's say we have a 3 by 3 matrix. Here, we're going to call this A1, B1, and C1. These will be numbers in any matrix, but for now, we're just giving them labels. And here, that's going to be A2, B2, C2. And over here, that's A3, B3, and C3. Like that. So now, let's say that that's the matrix. I'll just call it the matrix, I don't know, the matrix M. We've been using M for minors, haven't we? So let's say that's the matrix P. It doesn't really matter what we call it. Let's say that's the matrix P. Okay. Then we can define the determinant of P to equal to A1 times the minor of A1 times the minor of that number minus A2 times the minor of A2 plus A3 times the minor of A3. There are other ways of defining the determinant of a 3 by 3 matrix, but this one will apply even if you don't have a 3 by 3 matrix. The nice thing about this one is that it continues to extend even if you have a 4 by 4, 5 by 5, or 6 by 6. If we had one more row right here, we would say the same thing. It would just be, okay, now we'd have another run right here. We'd have an A4. Okay, well then we would use A4 times the minor of A4. If we had another row with an A5, okay, well then we'd have A5 times the minor of A5. This definition would work for any number of rows and columns, but for now we're just going to stick with 3 by 3 matrices. All right, so let's take a look at an example. Let's say we want to find the determinant of the matrix, let's see. We were using one just a moment ago when we found minors, so let's go ahead and use that one again. I'm going to say that's 2, 4, 2. 1 minus 3, 0, and minus 5, 5, and minus 1. Okay, so that's the same matrix I had before. And now the example is going to be, we're going to find the determinant. Here we're going to just use these bars instead of the normal brackets. When we have brackets here, that means that you have a matrix. But the bars around a matrix tells you to find its determinant. So here, instead of writing out the matrix with brackets and then separately saying, okay, now find the determinant, a shortcut notation is to just write the matrix, but instead of writing it with brackets, just to start off with these absolute value looking bars, and that means the same thing, find the determinant. All right, so here we're going to take that first number, that's going to be 2, times the minor of 2. Remember how the minor works. The minor is just ignore that row and that column. Whatever's left, take the determinant of that. Okay, well that's a 2 by 2 matrix. That's minus 3, 0, 5, and minus 1. Okay. And then there's going to be a minus here. And now you're going to take the second number in that first column, which is the number 1. And now you're going to take the minor of that number. So here, let's see what that looks like. The minor of the number 1 here. Well, again, you ignore that row and that column, like that. And what's left is 4, 2, 5, minus 1. So here we want the determinant of the 2 by 2 matrix, 4, 2, 5, minus 1. And finally, we want A3, this third number down here, which is a negative 5, times its minor. And again, when we look at the minor of negative 5, this number down here, we want to ignore that row and we want to ignore that column. And here, the matrix that is left, the 2 by 2 matrix, we're going to find its determinant is going to be 4, 2, minus 3, and 0. 4, 2, minus 3, and 0. All right, and now each of these are numbers that are simple enough to get. All right, that's the number 2. Here, that's negative 3 times negative 1. Well, that's positive 3. minus 5 times 0 is 0. Okay, well that's 3 times 2, which is 6. Minus 1 times, here we're going to take 4 times negative 1, which is negative 4, minus 2 times 5 is 10. And so that's going to give me negative 1 times negative 14. Well, that's a plus 14. And then I have, let's see, a positive of a negative. That's going to be minus 5. And now here, that's going to be 4 times 0, which is 0, minus negative 3 times 2 is negative 6. Here, negative of a negative, that's a positive. So that's a positive 6, and that's a negative 5. So that's a negative 30. And now 6 plus 14, that's 20. 20 minus 30 is negative 10. And so negative 10 is the determinant of this matrix here. All right. Just like that. Now, since we're only dealing with 2 by 2 and 3 by 3 matrices, let me show you one other way of finding the determinant of the 3 by 3 matrix. The 2 by 2 is nice and short, right? This times that minus this times that. There isn't any shorter way to do that. For a 3 by 3 matrix, this is a fairly convenient way of doing it because it breaks it down into small little determinants. And even though you have 3 of them, they're each relatively simple to find. Okay? There is a second way to do this. This works for a 3 by 3 matrix. And since that's all we're doing, 2 by 2 and 3 by 3, let's go ahead and show an alternate method. It doesn't give you a different answer. It's not really any easier or harder. You're going to notice it works very much the same way. It's got the same amount of effort. It's just a slightly different way of doing it. Some people prefer this way, and some people will prefer the other way. So I'm going to use the same matrix here. So that's going to be, I want the determinant of this matrix. All right, find the determinant of the matrix 2, 4, 2, minus 1, minus 3, 0, minus 5, 5, and minus 1. Okay. The alternate way to do this, take this matrix. Don't worry about putting any brackets or anything. You can, but it's not necessary. Go ahead and take it, write it down twice, right next to each other. Meaning, I'm going to write 2, 4, 2. And then again, I'm going to write 2, 4, 2. Have some even spacing here. Then I'm going to have negative 1, negative 3, 0. Negative 1, negative 3, 0. Negative 1, negative 3, 0. And then negative 5, 5, and negative 1. Negative 5, 5, and negative 1. Like that. Notice that's just the matrix. And then that's just another copy of the matrix. And I've just written them right next to each other like that. Oh, and I just realized I copied down wrong. I'm trying to use this exact matrix. That should be a positive one, not a negative one. So here, let me get rid of that. I want to compare the two exactly the same way. Okay, so there we go. Now that does look the same as my original matrix. Because that was a 1, not a negative 1. Okay, so now the way we're going to do this is we're going to take diagonals from upper left to lower right, and we're going to multiply. What I mean by that is you're going to take these 3 numbers, you're going to go upper left, down, over, down, over. You're going to take those 3 numbers and you're going to multiply them together. So 2 times negative 3 is negative 6. Negative 6 times negative 1 is positive 6. Okay, cool. And now you're going to move over and do it to the next set of numbers like this. So we're going to take 4 times 0 times negative 5. Notice, starting from this number, down and over, and then again down and over. All right, well, 4 times 0 times negative 5, that's just going to be 0. And we're adding those numbers. And then we're going to do it one more time right here. Starting from this number, down over 1, and then down over again. So that's going to be 2 times 1 is 2 times 5 is 10. Okay, so we're going to add all those numbers together. Okay, now we're going to do the same thing but going backwards. Meaning, instead of starting from this way going down and to the right, I'm going to start from this end going down and to the left. So here I'm going to have these three numbers multiplied together. Negative 5 times negative 3 is positive 15. Positive 15 times 2 is positive 30. Okay, now let's do the next number. Starting at 4, go down and over 1, and then down and over again. So that's going to be 4 times 1 is 4, times negative 1 is negative 4. And again, we're adding those. And then going back this way, all right, starting from this number, we're going to go down and over, and then down and over. Okay, so 2 times 0 is 0, times 5 is still 0. Okay, so all the ones that have the diagonals going upper left to lower right, you're going to add those together. All the ones that have diagonals going from upper left down to lower right, you're going to add those together. So all the ones going forward here, all the ones going backwards, add those together separately. Okay, so if we add those together, we're going to have, let's see, that's 10 and 6 and 0. That adds up to 16. And if I add these together, that's going to be 30 minus 4. So that's going to be 26. And finally, we're going to subtract those two numbers. So once you have all of these added together, separately you have all of these added together, the last step is to subtract. And here's 16 minus 26. Well, that's going to be negative 10, which you notice is the exact same answer we got before. This one has the advantage that you're using short, simple determinants that you know. But it is a little bit longer because you're doing three separate ones. This one has the advantage that it's a single computation. You start just multiplying and then at the end do a single subtraction. It has the disadvantage that it can get a little messy. It's a little hard to keep track for some people. Either of these mean the same thing. They both will work out. So it's a matter of personal preference. Some people like to do it this way. Other people like to use the minors. And so just choose whichever one you feel is convenient for you. So as our last problem of the section, go ahead and give this a try. Consider the following 3x3 matrix and find its determinant. You can do it whichever way you like. If you want to use the minors method, or if you want to use, I'm not even sure what the name of this is. I've never heard it named anything. But if you want to do the multiplying the diagonals, that's fine. It'll get you the answer. If you want to use the minors here, I misspelled minor here, didn't I? If you want to use the minors method, that will also get you the same answer. So pick whichever one you feel is convenient for you, and go ahead and find the determinant of the matrix. Find, and let's use the matrix 5, 1, 6, 2, 3, 4, 8, negative 1, 7. Okay. So find the determinant of this matrix. And here I'm using the shortcut notation. I'm not going to write it in braces. I'm just going to write it with the absolute value bars like that. Okay. So pause the video and go ahead and find the determinant of the matrix. And once you have an answer, unpause it and we'll go through it together. All right, so we can go ahead and find the determinant. Here I'm going to go ahead and do it this way. I'm going to go ahead and do the diagonals method. Both are fine. However, here we saw several examples of how to find small determinants using this. After all, minors really are just the determinants of 2x2 matrices. Here we only saw one example of this. So I'm going to do it this way. That way you have another example of that happening. All right. So, but of course, even if you did it the other way, we should still all get the same answer. So here we go. We're going to have 5, 1, 6, 5, 1, 6, 2, 3, 4, 2, 3, 4, 8 minus 1, 7, 8 minus 1, 7. Just like that. So now, I'm just going to start by multiplying those together. 5 times 3 is 15. 15 times 7 is 105. So 105. And then I'm going to multiply these together. So it's going to be 1 times 4 is 4. 4 times 8 is 32. And remember, those are being added. And finally, I can multiply these together. And that's going to be 6 times 2 is 12. Times negative 1 will give me negative 12. And all those get added together, which gives me, oh, let's see here, 137 minus 15 is 125. Just like that. And now I can go ahead and find the other set of numbers. And here I'm going to start from back here and work the other way around. So if I take 8 times 3 times 6, that'll get us 144. Plus, now let's go ahead and do these. We're going to multiply these together. And that's 1 times 2 is 2, times 7 is 14. And finally, these right here. Notice with a 3 by 3 matrix, all the ones along the top are going to end up getting used up. Some of the ones down here might not, but that's not a big deal. You're going to have 3 going one way, 3 going the other way. So that's going to be 5 times 2 is 20. 5 times 4 is 20. Times negative 1 is negative 20. And now if I add those together, that's what? 144 plus 14, that's 158. Minus 20, that's 138. Just like that. And then once I have these two numbers, I'm going to subtract one from the other. And if I subtract those, I end up with, let's see, 10, 13. Keep the sign of the bigger number. So here, that'll give me a determinant of negative 13. So here, find the determinant. It is negative 13. And that's our result. So that brings us to the end of our section. We are going to stop just shy of actually defining how to find the inverse. Remember, we began this section by saying the determinant of a matrix helps you determine whether or not it's invertible. It helps you figure out whether or not you can find an inverse. If the determinant is 0, you cannot find an inverse. But if the determinant is something other than 0, and it doesn't actually matter what that determinant is, you can invert it. So here, that matrix you can invert that matrix, you can invert this matrix as well. We're going to stop just shy of saying how to invert it because that's actually the beginning of another course. If you start talking about inverses, then you're talking about linear algebra, which is not something we're going to worry about here. So that brings us to the end of this section, and in fact, it brings us to the end of the chapter and the end of the book, the end of college algebra. So I hope you've all enjoyed the class, and if you haven't, well, I hope you all enjoy the fact that it's this is the end of it. So if anybody has any questions, comments, problems, make sure you let me know. You can visit the virtual office hour or or ask in the class. And I hope you all have a good day.